So let's begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So today we'll go over the contents of week 11 and discuss a few questions. But before that, we'll discuss the contents of week 10 and the assignment questions. Okay, so let's start. Okay, so let's begin with the recap of week 10. So that will help us solve the questions. So what was dynamic stability? Dynamic stability is when the aspect of time came into play, right? And for the longitudinal case, we had two equations, that is CL, the coefficient of lift, and CM, pitch movement coefficient. Okay, so initially we had the linearized versions of both of these coefficients involving just CL naught and CL alpha into alpha. Then when the control came into play, you had CL delta E into delta E. Similarly, for the pitching moment, right? When the dynamic stability came into play, we introduced two new terms. They were Q and alpha dot. What were the units of these two? What were the units of Q and alpha dot? What were the units? CL is a dimensionless quantity. It has no unit. So this entire thing and this entire thing must be dimensionless. So if you look at the quantities there, can you tell me what is the unit of Q and alpha dot? Unit of alpha is, what is the unit of alpha? It's radian, right? So what is the rate of change of alpha? Alpha dot, what is the unit of that? It'll just be radian per second, right? And what about Q? Yes. What about Q? It'll again be radian per second, right? So what is the unit of CLQ? What is CL alpha? Let's start with CL alpha. What is the unit of CL alpha? Such that this term becomes non-dimensional. Alpha is radian. So CL alpha will be per radian, right? Per radian, per degree, whatever, right? So what is CLQ? What is the unit of CLQ? Or how do you define CLQ? We discussed this even in the last session. CLQ, just CLQ is dCl by dQc by 2V, correct? So you should be able to get the units and the dimension from here. I will not be discussing this. Okay, so then due to a pitch rate, this is what we're discussing now. So due to introduced pitch rate Q, you have a change in the angle of attack, right? Change in the angle of attack at the tail. This is delta alpha at the tail. Because of an increase, or if there is an increase in angle of attack at the tail, there will be an increased lift component at the tail. It's given by this equation, and its non-dimensional parameter is here. Now, because of this increased lift, it will produce a pitch down moment, right? So we had discussed this in the last session. So delta M will be pitch down, and since pitch down is negative according to our convention, you have a negative sign here. Similarly, for C and Q, you have the negative sign. Okay. Then we saw how it related to a typical second order spring mass damper system, where CM alpha was like the stiffness coefficient and CMQ is like the damping coefficient. Okay. So CM alpha is the resistance towards any disturbance, and CMQ is the damping. So it tells you whether or not it will bring it back to equilibrium over time. As in, if you disturb it, will it come back to equilibrium over time, or if the damping coefficient is not sufficient, it will be uh, not come back to its equilibrium, right? It will deviate further, or it will keep oscillating about the equilibrium. Okay. Then we saw what are the different kinds of forces that are required for this analysis. We have aerodynamic, which is the lift and the drag, gravitational, weight of the aircraft, propulsive, thrust. And then we saw the two frames, that is the inertial and the body, and we saw the relationship between the two frames given by this transport theorem. Okay, so this is the transport theorem. Okay, you will be using it extensively in all of your dynamical analysis where you have more than one frame associated with the system. Okay, so why did we have to do this? Because some of the quantities we are measuring in our inertial frame and some of the quantities are measured in the body frame, while both the equations of motion, that is the linear and the rotation, that is the Newton's laws of motion and the Euler equations of motion, both of them are valid only in the inertial reference frame. So if you have quantities and the derivatives in the body frame, you need to transport it, or you need to transform them to your inertial frame, which is where this transport theorem is used. You can see it being used here. All right. So this is the body frame derivative, and the angular velocity component comes in to rotate it into the inertial frame. Similarly, for the Euler equation, this is the derivative in the body frame. This quantity converts it to the inertial frame. Okay. Then we saw the different quantities and their individual components in the frame. So you have force, VC, angular velocity. VC is the relative velocity, moment, angular momentum, all of them. Okay. Then we expanded these equations, this each component, and we wrote down the 6 equations of motion for dynamic stability of an aircraft. That is forces and moments, the 3 forces and the 3 moments. Just expanding these 2 gives you these 6 equations. Okay, so each of those equations was a vectorial equation. It had 3 components. So the first equation had 3 forces, second equation had 3 moments, which are given here. Then we saw the concept of Euler angles. Can someone tell me what Euler angles are? What is this phi, theta, psi? Where do we use them? What are they? What those notations represent? Can someone tell me? What is psi, theta, phi? What are Euler angles? Are there any other methods to represent angles? We had discussed this initially. I think 2 sessions we had discussed different kinds of representation of attitude or angles. Can you tell me some other methods, or can you tell me what Euler angles are? Where do we use them? Something about Euler angles. Well, angles are a way to represent the attitude or the orientation of the aircraft. So it is between, it's measured in which frame? So it's between the body frame of the aircraft and so these Euler angles are the orientation of the aircraft with respect to what? respect to the inertial frame, right? Yeah, and we had also discussed that these are not to be confused with the yaw or the pitch angles, which are measured in the body frame. Okay, so the orientation of the body frame with respect to the inertial frame is the Euler angles. They are not to be confused with yaw and pitch angles. Okay, and I had asked you this one question. We had discussed the answer to this question, but I'm just going to ask you again. So where do these Euler angles come into play? We had discussed that it comes into play in the gravitational forces and the angular velocity. This PQR is the angular velocity components. Okay, so in angular velocity you have the rates of the Euler angles, that is phi dot, theta dot, psi dot, all of that. In the gravitational components, only theta and phi are visible. Why is psi not visible? Why is psi not part of it? What happened to psi? We had discussed the answer to this, but if somebody can tell me, why is Xi not part of the gravitational forces? Why is Xi not part of it? It has something to do with the orientation of the weight of the aircraft, the weight vector, the force, right? So, is that helping? Why is Xi not part of the gravitational forces? How is the weight of the aircraft depicted? Vertically downward, right? So if it's vertically downward, will Xi come into play? What is Xi? It is not the yaw angle. What is the Euler angle Xi? Why is Xi not part of it? So if this is your X, this is your Z, this is your Y of the body. Okay, let me just do that again. X, Z, Y. So your weight is acting vertically downward. If after some time, if your X is here, Z is here, and your Y is here, your weight is still acting vertically downward, right? So weight is always acting vertically downward. Will the orientation in the Z axis with respect to inertial frame matter? Will it come into play? It's always acting vertically downward. It's always acting in that direction of the inertial frame, right? Okay, let's move ahead. Then from these 6 equations, we picked 3 equations and studied the longitudinal dynamic stability. All right. So, okay, this is supposed to be at the Z. All right. So, these are the 3 equations which are the same, just 3 from here in the longitudinal case. So, you have U dot, W dot, and Q dot. So, these are the 3 dynamical quantities that we will be analyzing for longitudinal dynamic stability. Okay. Then we introduce something known as a small perturbation theory to study this dynamic stability. What is a small perturbation theory? You take some point, some equilibrium point. For an aircraft, what is the equilibrium point? What is the equilibrium point for an aircraft? Can anyone define what is an equilibrium point? What is equilibrium? What is equilibrium and what is the aircraft's equilibrium point? We began this course with the definition of static stability. So it was defined as the tendency to go back to equilibrium if the body is perturbed, right? So there we use the word equilibrium. What is equilibrium? What is equilibrium? And what is aircraft's equilibrium point? Equilibrium is when sum of all forces equals 0 and sum of all moments equals 0. Correct? Can you tell me one such point for the aircraft? What is the equilibrium point of an aircraft? We're reaching the end of this course. So you should be able to tell me what the equilibrium point of an aircraft is. What is the equilibrium point of an aircraft? What is trim? What is trim condition? Trim is the equilibrium point of an aircraft, right? So what is trim? Give me one example or somewhere we have used this. Okay, let's move on from here. We'll discuss this again in the next class. Just try to tell me trim condition. What is trim? Steady level flight, remember? Lift equal to weight, thrust equal to drag. All of those conditions, steady level flight. Yes, that is the equilibrium condition for the aircraft. Okay. So, in the small perturbation theory, we consider the aircraft to be flying at steady state or the equilibrium state and then perturbed by a small quantity. So, all quantities with the subscript 1 are the steady state or the equilibrium quantities. For example, this U1, P1, Phi1, all of those. Okay, so those are the steady level quantities, equilibrium quantities. And the small alphabets, small u, small p, small q, all of those are the small perturbations. Okay. After this, we choose a stability axis. This is something that we discussed in the last two sessions. Stability axis is chosen such that our equations of motion are simplified. How choosing which such axis will simplify the motion is when you align the stability axis with the velocity vector. Because most of your quantities are measured either parallel or perpendicular, are defined either parallel or perpendicular to your relative velocity. Lift is perpendicular to velocity, drag is parallel to velocity. So such terms are simplified if you take the stability axis to be aligned with the velocity vector. Okay, so that is the only reason we choose the stability axis to be aligned in the velocity direction. Now, after all of these, the equations of motion are simplified and are written in terms of the small perturbations. And these are the three equations of motion for the longitudinal stability case, longitudinal dynamic stability. Okay. Then we analyzed each of those equations separately and we saw those individual derivatives. Okay. So these are the summary of the equations. And each derivative is calculated for each case. For the first case, we ignore quantities that depend on alpha dot. And there is no alpha dot here, alpha dot in Q. Though they are present, they are negligible and can be ignored. But in the Fz and pitching moment M case, they cannot be ignored. So you have 6 terms. You have 5 terms, 2 more terms. And individual derivatives are written here. And the final compact equation is given by this. Similarly, we perform this for W dot and Q. So this is the equation for W dot. And do note that here there is a negative sign. Why? Why is there a negative sign? Can someone tell me? We had discussed this last session and Sir had extensively talked about this. Why is there a negative sign there? I've written the reason in the bracket, but can someone articulate it? Why do you have a negative sign there? Why do you have a negative sign? Why do you have a negative sign there? In which direction, as far as the XYZ body frame is concerned, in which direction is the lift generated? The positive lift will be in the negative or in the positive Z direction. The lift is generated in the negative Z direction, right? So Z is downward, lift is due to generate upward. So that is why there is a negative sign there, because you have a CLQ, CL alpha dot terms, okay? All right. So this is the final equation for the Q dot. So you have U dot, W dot, and Q dot. So these are the three quantities. Then, so this is the compact form of the three equations and applying their Laplace transform, okay? So if you take the Laplace transform of this equation, you get Q of S equals S theta of S, correct? So if you use this and write the above three equations, the perturbed equations of motion, you get a compact matrix form like this, okay? So this can be analyzed using your AX equals B, where this matrix is A, this is X, and this is B, all right? And the characteristic equation for this matrix will be given by determinant of A equals 0. Okay. Now this gives you a fourth order equation, fourth order characteristic equation. That is, this is basically determinant of the A matrix. Not to be confused with this. Let's just call it cap. Let's just call that A bar. Okay. It gives you a fourth order equation. And to analyze its stability, we have three conditions. It's called the Routh criteria. So what are the three conditions? That is, all the coefficients should be positive. Okay. And then you have something known as the Routh table. Routh table, sir had discussed in the class. So from there, you get the other condition, right? So these are the conditions required, satisfying which the system will be stable. Okay. Now, the nature of these roots is such that you have two distinct pairs of complex conjugate roots. Okay. So you have two distinct complex conjugate roots that give you the short period and the long period modes. Long period is also called phugoid mode. So if your two complex conjugate roots are A plus or minus IB and C plus or minus ID, and let's say the magnitude of A is greater than the magnitude of C. So which one is the short period? Which one is the long period? Can someone tell me? Which one is short period? Which one is long period? If the magnitude of A is greater than the magnitude of C, which one is the short period? Which one is the long period? Which one is short and which one is long? The magnitude of A is greater than the magnitude of C. This is the short period and this is the long period, right? Okay. Now tell me if both the roots, if the system has to be stable, A and C should be greater than 0 or less than 0 for stability. For stability, should A and C, that is the real parts of both the roots, should they be positive or negative? Should they be positive or negative? If the system has to be stable, the real parts of the roots of the characteristic equation should be positive or negative. Will it be positive or negative? The real parts of the roots should be negative, right? For stability. Should be negative. Only then it will be stable. Otherwise, it will keep diverging. It will be unstable. Even if one of those roots is, even if one of the real parts of the root is positive, it will be an unstable system. Okay. Now you can get two separate equations for each of these modes, for the short period and for the long period, using their roots, and compare each of them with a simple second order system, with a typical second order system. And you can get the equations in this form, right? So for each of those modes, for the short period and the long period mode, you can have two separate comparisons with a typical second order system. Okay. And from there, you can see the natural frequency and the damping ratio. Okay. Now let's look at the questions of week 10. The characteristic equation for the longitudinal matrix is given as, it's a fourth order equation, the one that we just saw. The roots of the characteristic equation are. How do you find the roots of this equation? So this is quite a task. So what you do here is just, since the options are given to you, you just substitute those options, you just plug in those options in place of S, and you will get the roots, whichever solution gives you the value of 0 when substituted into this equation is the correct option. So just substitute each pair of roots. Just try all of them and tell me which one is the right option. Just substitute each set of roots and see which one satisfies the equation. So which one is satisfying the equation? I think it's this one, right? Yes. Correct me if I'm going wrong, but this, I think this value satisfies the equation. Okay, let's go on to the next question. The damping coefficients for the roots are, so for the phugoid and the short period, in that order. The first is the long period, second is the short period. How do you go about doing this? How do you do it? You need to find the damping coefficient. So I told you that each pair of roots can individually satisfy a typical second order system, right? So let's start with the first one. They've asked you for the phugoid mode and the short period. Let's start. So if you have two roots, how do you find the equation of the characteristic equation? You have s square minus sum of roots into s plus product of roots equals 0. Okay, and equate it to a typical second order equation. 2 eta omega ns plus omega n square equals 0. Okay, so what are the first pair of roots? Let's take the first pair of roots, this one. So 1.1595 plus or minus. So 1 point minus 1.1595 plus or minus 2.7894 I. Okay, now substitute it into this equation. What do you get? S square plus 2 into 1.1595 plus product of the roots. Quickly multiply and tell me what is the product of the roots. So I'm getting 9.125 equals 0. Now compare it to the equation above, typical second order equation. What do you get? You get omega n square is 9.125, which gives you omega n is square root of that 3.02. Then you have eta omega n. 2 eta omega n is 2 into 1.1595. So how do you find out eta? It is, we have 1.1595 divided by omega n, which is 3.02. How much do you get this as? What is the eta for, this is the short period, right? This is short period. Now we will do the long period after this. Yeah. So what is the value of eta short period? Damping ratio, damping coefficient of the short period? Just divide it and tell me. Getting 0.3838. Right? Okay, now let's do it for the long period. What are the roots of the long period? It is this. 0.2. So you have minus 0.0072 plus or minus 0.094. This long period. Again, form the equation, substitute it into this characteristic equation. You have s square plus 2 into 0.0072 s. And you have product of the roots. What are the product of the roots? What is it? What is the value? Just multiply those two roots and tell me. Correct me if I'm going wrong somewhere. Okay, so I'm getting 0.0082 equals 0. What does this give us? Omega n square is 0.0082, which gives us omega n long period is 0.09. And 2 eta omega n gives you 0.0072. And so eta of the long period is 0.0072 divided by 0.09. How much is this value? How much is the value? Just divide it and tell me. Zero point zero seven nine three. Yeah. So these are the two quantities. So which option is right? It's this. Correct? Now let's go to the next question. The natural frequencies for the roots are, we've already calculated the omega n. So what are the values? We have omega n, this, and this, right? 3.02 and 0.9. This is the value. Okay. Next, the given differential equation, what is the Laplace transform? Okay, how do you do this? Just take the Laplace transform of the first that equation. If you just take it, what do you get? S y of s minus y of initial minus y of s. And what is the Laplace transform of e raised to 3t? What is the Laplace? It's 1 by s minus 3. Okay. Now just simplify this equation to get the final answer. Do you get s minus 1 y of s minus y naught is 2 is 1 by s minus 3 s minus 1 y of s is 1 by s minus 3 plus 2. And so y of s is 1 by s minus 1 s minus 3 plus 2 by s minus 1, which option is it? It's the first one. Correct? Yes. Now the next question is, find the solution for y of t. Now that you have y of s, what was y of s? 2 by s minus 1 plus 1 by s minus 1 s minus 3. Okay, just solve this, find y of t. They've asked you y of t. So you're supposed to take the inverse Laplace transform. For that, you will have to take the partial fractions of this term. How do you do that? So you have y of s is 2 by s minus 1 plus a by s minus 1 plus b by s minus 3. Okay? Okay. Now do this and find out a, b. Find out the values of a and b, and then you can easily do the Laplace transform. What is a and what is b? The values of a and b. So I'm getting a as minus 1 by 2 and b as 1 by 2, right? So what does y of s become? 2 by s minus 1 minus 1 by s minus 1. Am I making a mistake somewhere? Two. This is plus 1 by 2 s minus 3. So what do you get that as? You get 3 by 2 into s minus 1 plus 1 by 2 into s minus 3. Now you take the inverse Laplace transform, you get y of t as 3 by 2 e raised to t plus 1 by 2 e raised to 3t. So this is the value. So which is the right answer here? 3 by 2 e raised to this is the one. Correct? Okay. Now let's try to solve this question. I think this was discussed in the last session, but let's just try to solve it. Now that you've solved something that's similar, can you try to solve this? Then we try doing it together. I'll give you a minute or two to solve it, and then we can try doing it together. First, you form the characteristic equation. So take y equal to e raised to at and substitute it into this main equation on the characteristic equation, find the roots, and then you can find the solution. Then you will have some constants of integration. You'll have some constants there, and that you can find out using the initial conditions. This one and this one, right? That's the sequence you need to follow. Try doing it, and then we'll do it together. Okay, have you been able to do it? Not, let's do it together. So if I take the characteristic equation now, what do you get? You get a square minus 5a plus 6 equal to 0. What are the roots of this equation? We can just do a minus 3 and a minus 2 equals 0. Right? So the roots are 2 and 3. 3. So now if I write the solution, what do I get? I get C1 e raised to 2t plus C2 e raised to 3t. How do you find out C1 and C2? You use the initial conditions. Okay, just substitute the initial conditions and you'll find C1 is 4 and C2 is minus 2. Let me know if I'm making some mistake here and just substitute it. So this is the final value you get. 4 e raised to 2t minus 2 e raised to 3t, which is this one, right? Okay, let's go to the next question. Yes, so this is something that we had discussed in the last session as well. And I had told you a simple way to solve this. Okay, so now let's try to find out the actual way to solve it. Okay, so what was the simple way? I had asked you to find the damping ratio and then compare it with the graphs of the equation and then find out. How do you find the damping ratio? Take the denominator and try to equate it to the typical second order equation. What is a typical second order equation? S square plus 2 eta omega n s plus omega n square equal to 0. Correct? Now tell me what's omega n is 3. What is eta? 1.5. So eta greater than 1 is overdamped. So which would be the graph? It would be this. But to get the exact equation, we will try doing this today. Okay. How do you do that? Let's take a fresh sheet. Now write down the transfer function. C of S by R of S is what was given in the question? 9s square. So 9 by s square plus 9s plus 9, where R of S is 1 by s. That is the input. Okay. So now what do you do? Again, take the characteristic equation and split it in such a way that you can find out either the partial fractions or some way to get C of t. What we need to do is get C of t, right? This is what we need to do. So now let's take the denominator and try to split it. So s square plus 9s plus 9. Okay. So what do we do here? And we know that eta is 1.5, omega n is 3. Okay. So how do you write that? You write it as s square plus 2 into 1.5 into 3 s plus 3 square. Correct? So now if we have to get something, if we have to split it in a nice fashion, just add and subtract. Let's just add 1.5 into 3 the whole square minus 1.5 into 3 the whole square. You'll find out why I'm doing this. Okay, now let's rearrange the terms. You have s square plus 2 into 1.5 into 3s, right? Plus 1.5 into 3 square, and then plus 3 square minus 1.5 into 3 square. So this is in the form of a plus b the whole square, correct? So it greatly simplifies our equation. So when we write it down, what we get is s plus 1.5 into 3 the whole square minus 3 square into 1.5 square minus 1. Okay. Okay. So now let's plug it back into the main equation. So C of S is basically R of S into, so it is R of S is 1 by S into numerator can be written as 3 square and the denominator is this quantity, which is S plus 1.5 into 3 square minus 3 square 1.5 square minus 1. Now this is in the form of a square minus b square, and that is equal to a plus b into a minus b. Correct? So what do you get? You get 1 by s remains there. Numerator is 3 square. Denominator becomes a plus b. So you have s plus 1.5 into 3 plus 3 into root of 1.5 square minus 1. So this is a plus b into a minus b. Okay. Okay, let me just erase this part of the equation. Why did we do this? Now we can find out partial fractions. How do we find out partial fractions? You write it in this form. A by S plus B by, so just calculate the values and you get S plus 7.854 and C by S plus 1.146. Okay, so C of S is equal to this. Now just find out A, B, C. What is the value of A, B, and C? And then you can directly get the inverse Laplace transform. What is A, B, C? Just find out. A is 1, right? B is what is B? Try to find out. What is the value of B? 0.1708 and C is I've gotten C as minus 1.1708. Now you can easily find out C of T. Where do I write this? I just write it here. So C of T, you take inverse Laplace transform. What do you get? You get 1 second. Yeah. So you get 1 plus 0.1708 e raised to minus 7.854 t minus 1.1708 e raised to minus 1.146 t. Right? So this is C of t and it matches perfectly with this value. So this is the right answer. Okay. So which is what we had got even with our simple analysis. That is, if eta is greater than 1, you had overdamped case. The only confusion was this was a similar graph. Okay, but if you superimpose both those graphs, you will find out that this is overdamped. Overdamped will come something like this. Okay. Okay. Now let's look at the next question. So the denominator has changed slightly. Now let's find out the new eta. Here, what is the value of eta? Just again do the same thing, s square plus 2 eta omega ns plus omega n square equal to 0. Omega n is again 3 and eta is 1. So it is critically damped. Now, since this was overdamped, this is critically damped. We know this, right? But how do we get the equation? How do you do it? How do you solve it? Let's do the same process. We'll start with C of S by R of S. That is the transfer function, which is, what is it? 9 by S square plus 6S plus 9, where again R of S is 1 by S. So what is C of S? We get 1 by S, 9, S square plus 6S plus 9. Can you split this into partial fractions and try to find out the answer, just like the previous case? It's simpler than the previous case, so it should be easy. Just try doing it. I'll give you a couple of minutes to do this, then we'll solve it together. Okay, let's try to solve this. What are the roots of this equation? This is actually simple. So let's just do this 1 by S, 9 by S plus 3, okay, S plus 3. So what will the partial fractions of this look like? It will be A by S plus B by S plus 3 plus C by S plus 3 square. Correct? So what are A, B, and C? Getting A as 1, B as -1, and C as -3. So now if you take the inverse Laplace transform, what do you get? C of t, you get it as 1 minus 1 into e raised to minus 3t minus 3t e raised to minus 3t. Correct? So that is the equation that is shown here. We had discussed this even last time because there are repeated roots. So in the critically damped case, you will have repeated roots, which is why there is this additional t here. Correct? Okay. Now for the next case, for the last case, this equation. What is eta value here? Omega n is 0. Oh, sorry. Omega n is 3. What is eta? What is eta? The same question that we had seen in the last class. Eta is 0. There is that middle term with s is not there, right? So it is undamped. Undamped, this should be the right answer. But how do you go about doing it analytically? Follow the same process. C of s by r of s is 9 by s square plus 9. So C of s is 3 square by s into s square plus 3 square. And you get what? If you take if you take partial fractions, you get 1 by s minus s by s square plus 3 square. You split it up, okay? So what is the inverse Laplace transform of this? What is C of t? It's very straightforward. What is the inverse Laplace transform? 1 minus cos 3t. Okay, so which is the equation given here. Okay, so this is how you analytically solve it. But if the graphs are given to you, you can also try doing it through some easy methods like finding out the damping ratio or see the nature of the roots and such. Okay. Now let's move on to week 11 contents. So we know that the main equation, this is the entire compact equation, right? So that ax equal to b. So we make certain approximations because usually the nature of the roots are such that they are very far away from each other. The two pairs are very far away from each other and we can ideally make a distinction. Okay. So the short period mode approximation is done by taking the assumption that u remains constant. If u remains constant, the first row and the first column can be eliminated. Okay. And you take just these parts of x and b. So your ax equal to b becomes a compact version. So ax equal to b. Okay. So this is the assumption that we make here. And then the second order equation of motion that you get is given by this. And upon solving it or equating it to the typical second order equation, you get the natural frequency and damping ratio like this. Okay. Similarly, we make a phugoid mode approximation. What we do here is that we assume alpha to remain constant. Okay. When this happens, what do you get? The second column and the third row are eliminated. Okay. And this is eliminated. All right. So here what you get is, this is the equation of motion that you get here. Again, when you equate it to a typical second order equation, you get the omega n, natural frequency, and the damping ratio. Now, a third case is the pure pitching. What is pure pitching? Pitching. So usually your pitch angle is what? It's gamma plus alpha. Okay. So if it's pure pitching, your gamma, that is the flight path angle, becomes 0. And your theta is just alpha. So this is the assumption that we are making. Okay. So with this assumption, these are the mathematical qualities that you get with this assumption. Okay. And when you substitute these into the main equation, you get the second order equation of motion given by this equation. And again, when you equate it to a typical second order equation, you get the natural frequency and damping ratio. Okay. And this slide summarizes the three approximations. You can see the three natural frequencies, three damping ratios, see how they are related to each other. Okay. So this is for the short period. This is for long period of phugoid. And this is for pure pitching. Okay. Now, let's see a few questions. So look at this question. It says, for an aircraft, the roots of the longitudinal characteristic equation are as shown in the figure. Okay. Now, can someone tell me what is the short period? What are the short period roots and what are the long period roots? So your two roots are -4 plus or minus 2 I, and you have minus 0.002 plus or minus 0.1 I. Okay, so which is short period, which is long period? Which is short period, which is long period? This is short period, right? And this is long period. Okay. Now let's look at the questions. The roots for the short period mode are, we just got this. What were the roots? Excuse me. 4 plus or minus 2, right? So it's this one. Okay. Now let's look at the next question. Natural frequency and damping ratio for the phugoid mode are respectively. So the roots for the phugoid mode were this. You find out the natural frequency and damping ratio. So the roots were minus 0.002 plus or minus 0.1 I. Okay. Can you find out the natural frequency damping ratio? I'll give you a couple of minutes to solve this. Okay, so like we said before, we'll just take S square minus sum of roots S plus product of roots equals 0, and then equate it to a typical second order equation, and then we can get it. It's very simple. So S square minus of, so sum of roots 0.004 S, and the product of roots is 0.0100 equals 0. So equate it to typical second order equation. What do you get? Omega n is 0.1, right? And eta is 0.002 by 0.1, and then you get 0.02. So they've asked you free natural frequency and damping ratio. Natural frequency is 0.1 and the damping ratio is 0.02. Okay, let's look at the next question. Consider the following equation for a system. Find the range of K values necessary for dynamic stability of the system. How do you do this? Okay, how do you do this? So one thing we know is that all the coefficients must be positive, right? So all the coefficients must be positive. So first condition is 1 plus K should be greater than 0. So K should be greater than minus 1. This is one condition. Now, what is the other thing? So I had discussed this roots table. How do you form the roots table? So if your coefficients are, this is A, B, C, neatly. So this is D. Okay. So if these are your coefficients, let's form the roots table. The root table is A, C, B, D, and say the coefficients are A1, B1. Right? Where, what is A1? A1 is minus 1 by the one above it, B. And then you take the determinant, A, C, B, D. Okay. So what is this? Minus 1 by 3. Let's just form this table. So A is 1, C is 3, B is again 3. This is 1 plus K, and this is A1. So for stability, what we need is that the first column, this is the first column, should be all positive. Okay, should be greater than 0. So A1 should be greater than 0 is the next condition. A1 should be greater than 0. So what is A1? We have 1, 3, 3, 1 plus K, which is 1 plus K minus 9 by minus 3. So it is minus 1 minus K plus 9 should be greater than 0. So what do you get? You get K should be less than 8. This is your next condition. Correct? Is this clear? I hope this is clear that the first column of the roots table should be positive, right? So this is how you form the roots table. Okay? Okay. So the two conditions, so which one satisfies both of this? K should be less than 8 and greater than minus 1, the first one. Okay? Oh, that's not the one. That's not the one. Do correct me if I'm going wrong. Be less than 8 and greater than minus 1. This is the one. Okay. So with this, we come to an end of this session. Does anybody have any questions? So this condition was given here. It's given here. So if nobody has any questions, we'll end the session here. We'll meet again in the next session. So all the very best for your exam. Thank you.